start by your point. Ekin answered his own question in during the break. So to rotate in 3D, you go to quaternions, something that is beyond complex numbers. Okay, it's written like this. Okay, so just a general knowledge. Let me erase this. Okay, let's talk about linear systems. So, for example, this first order equation that we have just seen is a linear system. It's a linear system. This is one of the reasons, but to me it's the most important reason. If x1 and x2 are solutions to this problem, to this equation, then so is actually any combination. Okay, let's not make a mistake right at the beginning. So let me call this K. So is C1 times x1 plus C2 times x2. Okay? Do you understand this? x1 and x2 are not the same functions. They are different functions. If x1 is a solution to this equation and x2 is a solution to this equation, then any linear combination, what does it mean, linear combination? It means that you multiply one of them with a coefficient plus the other one multiplied with another coefficient. So that should be also the solution. And we can show this. So what it implies that we already have this and we already have this. Okay? Do you agree? Now let's multiply the first equation with C1. So you get C1 times dx1 over dt equals K times C1 times x1. And you multiply the second one with C2. And since they are constants, you can just write it down like this. D over dt C1 x1 plus C2 x2 equals K times C1 x1 plus C2 x2. Do you see? That is also a solution. Any questions at this point? So you cannot do this with this equation. This is a nonlinear equation. Okay, and let's just do this one, dx1 over dt. Let's say there is one solution like this, there is another solution like that. When you sum them, you don't get this. Okay, left side is linear, but right side is not equal to x1 plus x2 squared. Do you see it? Does everyone see this? Yes? So what does it mean? It means that the linear equations are the ones that have these linear parts. So only x and constants are allowed. If you have x squared, x cubed, sine x, e to the x, yes, then it's nonlinear. Okay? And this effect is called, this thing is called superposition. Okay? So you can superimpose two solutions of a linear equation to get yet another solution, but you cannot do that for nonlinear systems. Okay? Do you have any questions? No? So this is what a linear system is. Let's also talk about second order ordinary differential equation. Okay, second order ordinary differential equation. For example, d squared x over dt squared is equal to k squared times x. Okay, so let's look at the right hand side. Is it linear, this part? Yes, because x is not x squared, it's just x. And this is just a coefficient. How about the left hand side? This is also linear. Okay, you can take the second derivative, third derivative, fourth derivative, doesn't matter. The system stays linear. Okay, but you cannot have x squared, x cubed on the other side. Okay, the system is still linear. So let's propose a solution. Propose a solution, and you can do this for ordinary differential equations in the form of e to the lambda t. So I'm just proposing that x could be this, and where does this proposition come from? It's an educated guess. I know that the derivative will bring just a coefficient, but the function will remain the same. That's why, so dx over dt would be just lambda e to the lambda t, and the derivative of that one will give me lambda squared e to the lambda t, right? Now that I have this, I can take it and put it back here, back in the equation. Lambda squared e to the lambda t equals k squared times e to the lambda t. Are you following? So turns out lambda can be plus or minus k. Okay? You look worried. Yes, you. Are you worried?
Yes.
You are also worried, but you are also worried. No? You are worried. What's the problem?
I couldn't understand.
Yes. Okay. Where did you get lost?
So we are just guessing a solution.
Yes.
X is probably e to the.
Yes, exactly.
And then we are taking derivatives. Right?
Yes, yes. And you are worried because what if, how will I know what to guess? That's your worry. Yes. It's always e to the lambda t. That's the answer. Okay? It's always e to the lambda t. Even when it's sign, you can write it down as e to the lambda t. So it's always e to the lambda t. You take this, you put it in, and you get lambda equals plus minus k, which tells you that there are two kinds of solutions here. There are two kinds of solutions. x1 equals to e to the kt, and x2 equals to e to the minus kt. Both of them work. Right? Exactly. Since both of them works, this one also works. So the general solution for this one is c1 kt plus c2 e to the minus kt. This is the general solution. And where are you going to get c1 and c2? You are going to get that from initial conditions, boundary conditions, initial conditions. Okay? That's the general solution. That brings us to the one and the only harmonic oscillator. Okay. Harmonic oscillator to physics is like Beethoven to music. Okay, it's central, it's right in the middle, it's everywhere. Sorry, I couldn't get the joke. But I hope you get the idea of importance. Harmonic oscillator is very important. So let's see what it is. And I will tell you why it is important. This is the simple harmonic oscillator. A mass connected to a spring. And we will talk about harmonic oscillator all the time. When we deal with classical physics, when we deal with quantum physics, when we move from classical to quantum, okay, harmonic oscillator is there. So, what is it? You can write it down as F equals ma. So F, the force, when you pull it, there is a restoring force. The more x increases, the more you have restoring force. And this needs to be equal to m times a, because F is ma, right? So m times d squared x over dt squared. The acceleration is the second derivative of position, right? So your equation looks like this. Okay? It's just like the other equation. Let me just continue juggling with this equation. You can write it down like this, where omega is square root k over m. Okay? Okay. You have this kind of equation, and let's compare it with this one. What's the difference? This was plus. This is minus, right? So you can propose a solution in the form e to the lambda t. It's always e to the lambda t. What do you get this time? So x, if x is this, then d squared x over dt squared is lambda squared e to the lambda t, which means that lambda squared is negative omega squared. Did you follow this? Yes? So lambda is either plus I omega or minus I omega. You see complex numbers appear. Wasn't for nothing. Did you follow this? Any questions at this point? Yes? Why we? Where did we delete it?
So the simple harmonic oscillator and matrix spraying system, the answer of the system is kind of like equal to a cosine omega t.
Oh yes, oh yes.
So we don't have any sign.
We do. Very good, excellent question. Excellent question. Let's talk about it. You see, you already see it. Okay. Yes. So, what is the general solution? General solution is C1 e to the I omega t, maybe minus I omega t plus C2 e to the plus I omega t. Okay? This is the general solution, and it seems like x has some complex numbers in it. But one thing that we should be careful about is that these guys can be complex numbers themselves. Okay, C1 and C2 can be complex numbers. And here's the thing, x and v are real valued functions. By v, I mean the velocity. Are you following? So let's do the following boundary condition. Boundary condition is this: x of 0 is x0, and dx over dt at t equals to 0 is 0. So you started the oscillator from some distance, x0, okay? This tells you that, first of all, at t equals to 0, x is c1 plus c2, and this needs to be x0. Do you agree with this? Yes? At t equals to 0, dx over dt needs to be 0, right? That's the boundary condition. And the derivative brings you what? Negative I omega c1, right? Plus I omega c2. Do you agree with this? So what is c1 plus, okay. What do we get from this? c1 is equal to c2, right? Which tells you that you basically have c1 equals to c2, which is x0 over 2. Then the solution is x0 over 2 e to the I omega t plus e to the plus I omega t. Okay. So what is this? Let me just put x0 here. And what is this? Some of you already know that this is cosine omega t. Okay. It could have started with a phase, in which case c1 and c2 are going to be complex numbers, but they are going to be complex conjugates of each other. And as a result, you are still going to get a real number. Okay? It might be in the homework, so that's why you are going to get used to it anyways. So far, so good? Any questions? I hope you had a good lunch and you are in a good mood, because I will ask you to take a leap of faith. Take a leap of faith. That you can do this, you can understand this. And let me write one sentence, and we are going to try to understand this sentence. There will be a lot of words that you don't understand. Okay? Hermitian. Oh, thank you very much. I keep doing it. Matrices. Exactly. Have real eigenvalues and their eigenvectors form a complete orthonormal basis. Okay? Let's try to understand this sentence. Okay? We will go over. So, who understands 100% of it? Yes? Some people? And then there is a spectrum, right? 10%, 20, 30, 40, etc. We will start with matrices. Okay, Hermitian matrices. So let's start with matrices. Let's start with vectors and matrices. And this is where we are aiming. Why? You will understand once we are doing quantum mechanics. Okay? Good. Vectors and matrices. So here is a vector 1, 2, 3. This is a vector collection of numbers in a column. Okay, and here is a matrix 1, 2, 1, 2, 1, 1, 3, 1, 3. For example, this is a matrix. Okay, let's do something. Let's say A is equal to 1 minus 2, 0, 3. Sorry. B is equal to minus 2, 1, 3, 4. Let's calculate A times B. Do you remember how to do this? So what you do is you multiply this one with this one and you write it down here. This one with this one, you write it down next to here. Yes? That's how you keep going. So let's do it. Let's multiply this row with this column. So how do you do that? You actually multiply 1 by minus 2 plus minus 2 times 1. What do you get? Minus 4. I do trust you. Minus 4. So what are the other ones? I already have them here, so you can maybe check them. This is what I get. Can you quickly check that, please? Now let's calculate B times A. Okay. Then for this one, I take this one first, and that one second. Surprise, surprise, doesn't give the same answer, right? Turns out to be negative 12, negative 2, sorry, 13, 1, and 10. Okay. This is when we say that A and B do not commute. So A times B is not equal to B times A. Okay? You will hear it many times in this course. Let me say it for the first time. Matrices are like operations. Okay? Let me give you an operation. You turn the what is this? Can I say wheel? You turn the wheel. It's fine, right? You turn the wheel and you press gas and go forward. These operations do not commute. Okay? Let's say I start here, I turn the wheel, and I go forward and I end up there, right? Versus I go there and turn the wheel, so I end up there. Do you see this?
You load the gun then shoot.
Yes, that's another non-commuting thing. You load the gun and shoot, or you shoot the gun and load. Okay? Given that you have one bullet, they differ. Okay. Even if you have many bullets, it's different, right? Very good. Very good. Or you take the Rubik cube, okay, and do this and then do this. Okay, versus doing this and then doing this. They are different. But take the Rubik cube and do this and this versus this and this, they are equal. So these operations in the Rubik cube do commute. It doesn't matter which one you do first. Okay? Let me spoil where it all goes. You must have heard of Heisenberg's uncertainty principle. Okay? We will see that position operation and momentum operations, they do not commute, and that's why you can't measure them simultaneously at the same time. Okay? Because it matters which one you measure first. But whenever it doesn't matter which one you measure first, in terms of mathematics of quantum mechanics, then you can measure both simultaneously. That's where we are going, okay? So it is all connected, nothing is going to waste. Good. Very, very good. What happens if you multiply a matrix with a vector? Let's do that. So let's say you take a matrix 1, minus 2, 0, 3, and you multiply it with a vector. So this is a matrix. This is a vector. So you can still multiply rows by columns. So what do you get at the top? Minus 3 at the bottom? 6. Okay, good. So you can think of it this way. You took some vector and your matrix operated on that vector to make it another vector. This operation can be rotation, can be scaling, can be flipping, that kind of stuff. Some sort of operation. And some of these operations commute, some of these operations do not commute. Good? Any questions? No? Okay. Let's talk about Hermitian matrices, what they mean. First, let's remember what is transpose. What do we mean by transpose? Let's say you have 1, 2, 3, 4. When you take the transpose of this, you get 1, 3, 2, 4. So rows become columns, columns become rows. Okay? This is transpose. Hermitian conjugate, I will keep doing this, I guess. Conjugate, B12 deficiency. Hermitian conjugate is the following. You take the complex conjugate and you also transpose the matrix. Okay? Let me give you an example. 1i, 2i, 3. So it's the Hermitian conjugate is shown by dagger, something like this. So you take the conjugates. Let's take the transpose and take the conjugates later. So this is the transpose. And to get the conjugates, you just make i's minus I, right? So this is what a Hermitian conjugate is.
If there's a complex element in the diagonal, it also gets conjugated, right?
Yes. So you get transpose and you get conjugate element-wise conjugation. Does this make sense? And it doesn't matter which one you do first. Okay, good. So we are about to understand the first word. The first word. Hermitian matrices are matrices which have this property. Okay? When you take the Hermitian conjugate, it's still itself. Okay? Let me give you an example. 1 3i minus 3i 2. What do you get? Let's take the transpose 1 minus 3i 3i2 and then conjugate, so you get the same thing. Do you see? This matrix is Hermitian. Let me spoil one more thing for you. Why we care about Hermitian matrices? Because everything that we can measure in nature correspond to a quantum mechanical Hermitian operator. The corresponding operators, matrices that correspond to measurement of position, measurement of momentum, they are going to be Hermitian. Okay, that's why we care about this. All right. So basically, if you want to spot a Hermitian matrix right away, look at the diagonals. So the diagonals should be real. They can't have complex parts, because if it's, for example, 1 plus I, then when you take conjugation, these diagonals will stay in the same place, and it will become 1 minus I. So it's not equal. And also, the off-diagonal elements should be complex conjugates of each other. Okay? That's how you can spot it. So far, so good. Let's now talk about eigenvalue equation. Sure.
When we compare the definition of the Hermitian matrix with this Hermitian conjugate equation, it's an if conditional, it can only be conditional.
Okay. What do you mean by that?
I mean, in the upside, we wrote the definition, and for the Hermitian matrix, this one.
Okay.
For this definition, when we say A Hermitian conjugate is equal to A, they are equal to each other.
So Hermitian matrices are those matrices who have their Hermitian conjugates equal to themselves. Okay, and those matrices, those kinds of matrices, have real eigenvalues, etc. Okay, I'm really bad in this logic kind of stuff, if and only if versus if. The thing is that I'm too cautious, and that makes me very, very slow. I don't mean that I don't get it. I just very cautious to not make an error, so that it makes me slow. So, okay. Eigenvalue equation, yes?
So I'm not sure if it's named matrix, but does all matrix count as a Hermitian matrix?
If the matrix has the symmetries that I mentioned, meaning that it has all real diagonals,
Yes.
and off diagonals are conjugates, complex conjugates of each other.
If it does not have complex number.
If it does not have complex number, then their real values has to be equal to each other, right? It has to be symmetric, yes. It has to be symmetric in real values, anti-symmetric in a sense that minus plus in the complex parts.
For example, we have a matrix do not have imaginary number.
Mm-hmm.
So it can be Hermitian.
It can be Hermitian only if you have 1, 2, 3, 3. Because when you transpose it, it still needs to be equal to itself.
For example,
This one is not Hermitian. Yes.
I know I couldn't understand the difference between Hermitian conjugate and matrices. It
Yes.
looks like
Yes. I see what you mean. So Hermitian conjugation is an operation that you do to the matrix. Okay? You have a matrix, any matrix can be Hermitian conjugated. You can take Hermitian conjugate. But after you do Hermitian conjugation, if it's still the same matrix, if it didn't change after Hermitian conjugation operation, then it's a Hermitian matrix. Okay? Very good question. Thank you very much. Any other questions? No? So, eigenvalue equation. How does eigenvalue equation look like? It looks like this. There is a matrix times a vector equals to a number times the same vector. These are the same vectors. This is a number. This is same vector. And this is the matrix. Okay? What does it mean? Usually, what it means that, okay, A is a matrix, which means that A is doing some operation, right? Given the matrix A, we are looking for those vectors that upon operation stay in the same direction. It can go to the negative, it can go to the opposite side, can grow or shorten, okay? But it stays, sorry, not direction, orientation, same orientation, okay? Okay. So, operation times vector is equal to number times vector. And these vectors, so given the matrix, its eigenvectors are these vectors, and these numbers are its eigenvalues. Okay? We will figure it out. So let me show you how you do this, how you solve this. To figure it out, to solve this kinds of eigenvalue equation, you need to do determinant of A minus lambda times identity matrix equals to 0. Okay? What is identity matrix? Identity matrix is, let's say, 1, 0, 0, 1. This is an identity. Or if your matrices are three-dimensional, then it could be. So it's all ones on the diagonal, all zeros everywhere else. All these are identity matrices. Okay? So to solve this, you need to do this. And the best way is to do an example. Let me do an example. This is an example. I will look at this matrix, 1, 0, 0, 2. Okay? I want to find its eigenvalues and eigenvectors. By the way, is this Hermitian? Yes, when you transpose, conjugate, it's still the same matrix. So, I'm going to do this, determinant of A, which is 1, 0, 0, 2, minus lambda times identity is equal to 0. That's what I'm going to solve. Okay? Which is, let me write one more step, or let me not write one more step and see whether you have problems or not. Do you have problems? Or do you understand? Yes? So determinant of this one should be 0. Do you remember how to get determinants? Yes? You multiply, oops. No, I don't want that. I want this. You multiply this one with this one minus this one with this one. So let's do that. 1 minus lambda times 2 minus lambda minus 0 times 0 is equal to 0. What are the roots of this equation? Lambda 1 equals to 1 and lambda 2 equals to 2. Okay? Now, what have we accomplished? We found eigenvalues of this equation, of this matrix, eigenvalues. Okay? Let's see where we are in the sentence. Hermitian matrices have real eigenvalues. Do you see? Indeed, we took a Hermitian matrix, we found its eigenvalues, and they are real. Good, right? Not too bad for 40 minutes. Real eigenvalues. Now it comes time to find eigenvectors. How do you find eigenvectors? So let's choose one of the eigenvalues, and we know that A times the matrix times this vector, the first eigenvector, needs to be eigenvalue times the vector. Okay. Okay, I have digressed here a lot in my notes. I think this digression is too much, so let me just feed it to you like a formula directly. So basically what we do is we take 1 minus lambda 1, 0, 0, 2 minus lambda 1, and we try to find V1 that would make it 0. Okay, we are looking for such a vector that would result in 0, 0. That's what we are looking for. Right now what I'm doing is I'm trying to teach you how to do it. This is exactly how you do it. Find eigenvalue, put it in this form, and figure out what V1 can be. Okay, 1 minus lambda 1 is 0. This is 0, this is 0, this is 1. And there is some vector, let's say AB, that results in 0, 0. Okay? So, I know what you are thinking. You can multiply 0, 0 by AB and you will get 0 anyways, no matter what it is. And the rest part is you can multiply 0, 1 with AB and you are going to get B, which must be 0. So the only information that we are getting from here is that B must be 0. Okay? But that's a very important information. So we got B equals to 0, which tells you that the eigenvector is in the form A0. But this is fine, because here's why it is fine. Let's remember the eigenvalue equation. This was the eigenvalue equation, right? Can I multiply both sides with any number? Yes. So I can have 3 here and 3 here. Then 3v is also eigenvector. Do you see it? So we don't care about there should be a coefficient unresolved in this endeavor, and that coefficient is A. So what we say is that V1 is 1, 0, and it can be multiplied with any number, okay, and it will still give you an eigenvector. Okay? Okay, we have 1 minute left, so let's continue from here next time. Do you have any questions? No? So please study these parts. Next time we will continue from here.